Hey, IB Physics kids, Mr. Tima back with you. Section 4.2, gravitational fields and orbits, okay? This is the fundamental stuff. We're going to see this stuff kind of come up in future chapters, at least two others. So you're going to see this chart that I'm going to keep building to compare them to each other. But we're basically talking about Newton's law of gravitation here. All right, there's our assessment statements. You want to pause those. You can take a look at those when you're studying for your IB test. All right, but basically it all comes down to this. Hopefully you've kind of realized that we started out with one-dimensional motion, so an apple falling towards the surface. We have suvat, 1/2 at squared, things like that. But everything in the universe truly is either rotating, revolving, something like that. So what Newton said was there has to be a relationship between these center-seeking objects. Everything is seeking towards the center, if you will, okay? But depending upon your field of reference, is it one-dimensional? Or is it rotational? Is it tangential? Things like that. And basically, what he said is everything in the known universe is acting on everything else. It's a very symbiotic relationship, this idea that everything affects everything, but there has to be some guiding principles. Well, he came up with this equation right here. And basically, with this equation, he said that F, the force, okay, is equal to the mass of one object with the mass of another object with the radius squared. So there's got to be some relationship between the masses of these two objects, like this planet and this planet, and about the radius or the distance, the displacement between them. And then he had to come up with, and this is the real science, this G. And what G is the gravitational constant. And G is a constant that you will use, and it is 6.67 times 10 to the negative 11th power. Okay, and that is actually a Newton times meters squared, okay, divided by kilograms squared. And that's kind of a big unit. We don't tend to use that unit very often because it kind of comes out in the math, if you will. But this 6.67 times 10 to the negative 11th is G. And if you think about it, usually we're talking about planets with newtons, and those are huge masses and a huge radius. So we have this constant that kind of brings it back into fundamental units that we can understand. All right, so here's an example. If you have a mass of one planet, a mass of another planet, or something even as small as a ball or a dumbbell on Earth. I mean, this is the mass of a planet, okay, the mass of an Earth. It's the mass of Earth and a mass of an apple, okay, very different. But yet we can calculate the force that that apple feels due to the mass of the Earth by following this equation right here and inserting that constant. And from that force with the mass of the apple, we can then calculate the acceleration of gravity, which we know is 9.81. Well, if you do that math right here, you're going to see that that's 9.79, pretty dang close. So again, this is how we can calculate the acceleration due to gravity on many planets as compared to Earth. So again, we have this guy going on here. Again, just walking you through how they calculated that again. All right. So again, if you have the sun, and you have the Earth, and you have the radius between them, you plug and chug those into this equation using that G, that 6.67 times 10 to the negative 11th, and you get the amount of force we feel, or the planet Earth feels, from the sun. We're not going to do this, this simulation. If you want to, you're welcome to mess around with it, but we're not going to do that one this year. But it kind of walks you through how to calculate that velocity using the v squared over r. You can calculate the centripetal velocity, because remember, mv squared over r is the centripetal force, centripetal force that we talked about in the last section, 4.1. So here's our chart. What I did is I took the gravitational relationship and I put it all in here. So gravitational field strength is based upon the symbol G. It's caused by masses. It's affected by masses. It's all about the mass, and it's attracted by masses. So this idea of how we can calculate that field strength, how we calculate that field strength. And I love that this little bar thing. Oh, I guess I could hide it, right? All right, that field strength kind of, we're solving for that thing. So again, field lines. This is very important. Field lines, okay? So field lines. On a sphere, we have to assume that they're coming in at all different angles and everything like that, okay? Because it's a sphere. They come in from all directions. But when we get closer to the Earth, we assume it's very planar, as if they're moving just from up to down or down to up in a very thing. We call this a uniform field and this a spherical field. Very important about fields, okay? Very important about fields. I'm going to get to a different color. I thought I did. Oh, pen color. Duh. Goodness. All right, I'll go with, let's go green, see if that shows up. All right, positive field lines. Positive charges on a field lines radiate outward. Negative charges have field lines that radiate inward. How do I remember that? If you're a positive person, your energy always seems to radiate outwards. It's like you spread your positivity almost in an annoying way. Some people that are super positive almost are annoying. If you're negative, it seems like everything comes in on you. It's like, oh God, this happened to me, and this happened to me, and Mr. Tima assigned me homework, and blah, blah, blah. You get very negative, feel like everything's coming in on you. So that's how I remember it. Positive outward, negative in on you. The electric field is always tangent, again, at a right angle. If you remember that from circular motion, everything leaves at right angles. That's very important. All right. And the number of lines equals the strength of the field. So these fields would be equal to each other. The strength of them would be equal because there are 8 lines, 8 lines. If this guy had 16 lines and this guy only had 8, this negative field would be stronger. Okay? Again, since they are vectors, since they move at right angles, they can be added like vectors. All right, so here we go. Let's look at this problem right here. Now, this is not comparing. This is not just m1 v1 over r squared times the g. This is asking about field strength at point A and point B. So the way to think about this is, if I was in a spaceship at A, what would I feel? If I was at a spaceship at B, what would I feel? So how do I do this? Well, the first thing we have to do is the gravitational field strength at A is equal to the sums of this planet acting on you and this object or planet acting on you. So what would you do? Well, the field strength due to the large mass, or we're just going to call, we'll just call this the large mass right here, is right here. You can follow along. That's the mass of that object, and the r squared, this is the r to the a, we're only talking to the a here, okay, is right there, and you get this. The field strength of u due to this mass is this mass, 100. It's the same radius, right? There you go. And we get this. Now, the question is, how much are you experiencing? Are you going to add these two forces together? Or are you going to subtract them? Remember, you're on this spaceship right here at point A. Are you going to add the strengths of these two? Or are you going to subtract one from the other? The answer is you're going to subtract them. Why would you subtract them? Why would you not just add these two together? Well, the answer is, right, if you're on the spaceship, you're actually kind of getting pulled this way, and you're getting pulled this way. So if you're going to call this guy positive, then this guy has to be negative. Or if this guy is positive, you're going to have to call that guy negative. They're in opposite directions. So let's think about this for a second. What if we were at point B? What if we were at point B? You do the same process again. Now the numbers would be slightly different, right? Because B, right, this wouldn't be 2.5. What's the radius? What's the radius from the large mass? It's not 2.5, it's only 1, okay? And then again, what would be the radius out here to the 100? It wouldn't be 2.5, it would be 2.5, 2.5 is 5, that would be 6. Okay, so we'd have new numbers here, right? But these two new numbers, aren't both of them being pulled basically? Aren't you being pulled this way? And even by a little bit, you're being pulled this way, right? So they're in the same directions, So you would actually take whatever this new number is and whatever this new number is, and you would add them together to get our total. Okay? Hopefully that makes sense. If you have a question about that, make sure you ask me that in class. So how do we finish up these notes? Well, very simple. We're going to do a really cool thing where you're going to have to put a puck into a net using field strength. That's going to be a lab for us to do. And then finally, the last thing we're going to do is you have a couple homework problems. What is that? 1, 2, 3, 4, 5. You have 5 homework problems. So again, we're going to do a lab, which is a lot of fun. And then we have some homework problems. Until next time, everybody, okay, Mr. Tima is out of here.